So today I want to talk about intermolecular forces, do a couple videos on there. First of all, when I say intermolecular forces, I'm talking forces in between two molecules. Like for instance, say I have two water molecules. They're going to come in so that the hydrogen on one water molecule is going to be kind of have an interaction with the oxygen on the other. So again, it's not within the same molecule, it's within two different molecules. That's what I mean by intermolecular forces. So I kind of made a quick diagram of it. So this hydrogen will be kind of bonded with that oxygen. And again, the reason is that hydrogen has a kind of a positive charge, and that oxygen has kind of a negative. So again, remember, it's between two different molecules, three different molecules, etc. It's not within the same molecule itself. So these are intermolecular forces. They'll affect everything from boiling point, vapor pressure, polarity. So there's a lot of things, solubility. So there's a lot of things that are affected by intermolecular forces. We're going to look at four types. First type is ionic. This one is easy to identify. It's just within an ionic compound. So ionic compound will have a metal in there, like sodium chloride, potassium nitrate, etc. So this is where you have to know your polyatomic ions to identify these ionic forces. The second one is hydrogen bonded. Hydrogen bonded, you got to be very careful. It's only between the oxygen and hydrogen, nitrogen and hydrogen, and fluorine and this should be hydrogen, sorry, fluorine and hydrogen. So not everything is going to have hydrogen bonded. A carbon hydrogen bond is not hydrogen bonded. It's a very strong type of intermolecular force, and the reason is because oxygen, nitrogen, and fluorine are the three most electronegative elements. So they'll have this negative, and then you have that positive on that hydrogen. Again, water is probably the classic example of that. Hydrogen bonding, again, it's going to be for polar molecules. The other one, dipole-dipole. Again, this is for polar molecules. So one end will have partial negative, the other end will have partial positive. Some good examples of it, hydrogen chloride. So again, notice in this case, even though there's a hydrogen, it's not hydrogen bonding because it's not bonded to the oxygen, nitrogen, and fluorine, but does have a negative on one side and positive on the other. These carbonyl groups, the C double bond O is a carbonyl. These are classic, dipole-dipole. Carbon is not as electronegative as the oxygen, so partial positive here, partial negative there. And you remember, it's always negative and positive that have that interaction. So that dashed line, that's the intermolecular force. So ionic compounds are going to have ionic. Polar compounds can have either hydrogen bonding or dipole-dipole. And then the last type are London dispersion forces, LDF. These are only, or I should say, nonpolar molecules only have London dispersion forces. There is a rule that says that all molecules have London dispersion forces. When you look at this, basically, we're always interested in the strongest type. So even though, like hydrogen bonding, dipole-dipole, those molecules normally are going to have some type of London dispersion forces in addition to their other types of intermolecular force. We're always interested in the strongest type. So if you have a nonpolar molecule, London dispersion forces is the only type that's there. One thing about this, when I'm comparing strengths of London dispersion forces, it has to do with the size. Higher molar masses, the stronger the London dispersion forces. Because the bigger something is, the more those electrons in those atoms can shift. You have a partial negative and partial positive. Remember, LDF is instantaneous dipole. It means just for a fraction of a second. So even though iodine is nonpolar, just for a fraction of a second, the electrons could be shifted on one end or the other. So one of these iodines can have a partial negative and a partial positive. Again, only for a fraction of a second. Dipole-dipole is permanent. Hydrogen bond is permanent. Ionic is permanent. So these interactions are the weakest of them all. To make it simple, ionic is the strongest, then hydrogen bonding, then dipole-dipole, and then London dispersion forces. In most cases now, when I ask you these questions, they'll ask you, what's the strongest type of intermolecular forces? The stronger it is, normally higher, we say boiling point, freezing point. Not always. Molar mass has a big thing to do about it. So, and normally, in most cases, we'll say that the higher the molar mass, the higher the boiling point and freezing point. So we have things to consider. If two molecules are the same size, basically the same molar mass or close to it, their intermolecular forces decide which one has a higher boiling point or freezing point. If one is much larger than the other, and then that larger one with a higher molar mass, that's going to have the higher melting point and boiling point, etc. So again, you got to make this comparison between molar mass and intermolecular force. We'll go through examples to kind of make that clear, hopeful. Other things that are affected by intermolecular forces, vapor pressure. Normally, the stronger the vapor pressure, the stronger the intermolecular force, the less vapor pressure. We use VP for vapor pressure. So vapor pressure is things that go into the vapor phase. If you have very strong intermolecular forces, it's hard to break these intermolecular forces to form a gas. So again, you have to break intermolecular forces to go from a solid liquid to gas. Strong intermolecular forces are kind of hard to break, and it's hard to vaporize with that. So you have low vapor pressure. If you have a strong intermolecular force. And again, we'll go through this in a bit.